Thank you. Thank you, Habit, for the introduction. A bit of introduction of myself. I'm Dea. My background is in statistics. I'm a statistician. I think you will be surprised as well why Philip Morris International is attending this conference. So the idea behind it is that I would like to give a bit more a feeling of like we're always talking about this huge data, how to use the data, the analysis and so on, but how do we as an industry is actually doing something about it? Because maybe some of you, if you're a student, you always thought like, how am I going to really use all what we studied here in the university in real life? And voila, here I am to give you a bit of a showcase of what is actually can be implemented of all this coding technology, the Python, R, statistical models, and so on. So please bear with me. I chose the title for this topic is Beyond Confidence. How then we move away from confidence intervals and use again the cousin, which is tolerance interval, when we want to make a data-driven change. Here I'm going to go through this stage, so I will first come to the introduction part, giving you a bit of the problem context in the industry. Then we are moving a bit on the introduction to what the intervals 101. We know 3 different kind of intervals: confidence, predictions, and tolerance, and why we then end up choosing the tolerance interval. I will also give you a bit on the case studies where we are specifically looking into nonlinear curves, and I will also walk you through on why this nonlinear topic is something that is important for us. And then a bit of practical workflow for the tolerance interval usage in the industry, a bit of conclusion, key takeaways, and then I will let you ask your questions. This is how our office looks like in Neuchâtel in Switzerland. A bit of the context, my team is called Design Verification System and Consumables. So you might also a bit wondering why a tobacco company is also now moving into a system and this kind of engineering stuff, because as we are moving away from the conventional cigarette and then move to the smoke-free product, we introduce all this advancement using the technology, and that's where our approach is more closer and closer to any engineering industry, where we try to verify more rigorously the new designs. And when I say designs is not just the look of it, so it includes as well the changes of the supplier, the changes of the heating technology and so on, against what we determine as well as a reference standard. So the objective on why we have statisticians in the design verification is mostly we try also to have a robust definition on what is comparable. So what the new design that we can ensure the performance reliability in most of the nonlinear systems. The challenge is when design change, even slightly, you're saying like maybe it's just a changes of a little blend. Instead of using plastic, now you're using paper. So all these little changes actually making it difficult for us to define in a scientific question, how can we say that this new product is comparable to our reference product? And when we are talking about comparable, we cannot just talk about the average, because average is just some parameters, some parameters about our population. But in reality, when we talk about design verification, we want to make sure that a certain population, a certain proportion of the population of our product actually will meet this criteria, because that's what we promise to our consumer. So then we need a statistical method that look also into the entire distribution instead of just certain parameters. So what we have as a core question is that how this new design can we claim statistically comparable to the reference product and measure it, and we make a conclusion across the full performance profile instead of just talking about the average. So when we are building this kind of verification against the established reference standards, in engineering system, we are so often going away from linearity. I think linear is nice when you're in a classroom, it's very easy to compute and so on, but in reality, this is something that we rarely see. So that's the reason why it gets a bit more complicated in reality, because we have to move forward from everything that is simple to compute, easy to estimate, to a nonlinear that it's every kind of pattern can change slightly differ. So the people also tend to avoid nonlinearity because before we have a limitation in terms of computation. But with 2 days computational capacity, we are also getting closer and closer to the nonlinear approach, because then we have this luxury of not running your algorithm for 2 days anymore. So then giving you a bit of the examples of when this nonlinearity pattern can be observed is, in our cases, for example, we are measuring the aerosol deliveries, how consistent the emissions over the time. You might also know the battery system, how this energy is discharged and released over the usage. Insertion extraction curves when you are inserting the ICOS stick into the machine, into the device. So all this stuff actually just giving you an example why we're moving away from the linearity to the nonlinear model. So in statistics, if I can summarize, there are these 3 methods that are so common. For example, if you are hearing about statistics, you normally talk about mean comparisons, where we are only focusing on the average performance of our population, comparing, like, let's say 2 groups, reference to the test group, or you sometimes even have more comparisons group. But the limitation when we're just comparing mean is that it hides also, we don't really look into outliers, which is very common in reality. We don't see the high variance, which normally also influence failures. The second part is that we're also then, after we compare means, we normally talk about as well the intervals around it. So we normally just build point-wise intervals, like let's say you do a measurement 7 times over a usage of 7 different usage, you compare it point per point, but then this discreteness also ignoring how, in reality, the pattern, when we look at it in a continuous nonlinear way. The third part is with the sample matching. So in the industry, it's really, we cannot just observe how many samples as we want. First, we are talking about resources. Resources meaning the human also who get involved in the sample preparation, doing the lab tests and so on. We're also talking about the costs. So all the statistician dreams is to measure the population, but in reality it's not gonna be happening, especially when you are working in the industry with tight budgets. So then how then you ensure this few key samples is actually quite representative to our general population, so that this kind of approach with just taking a sample and then you look into certain parameters, it will then will be sufficient for us to understand how is the large fraction of our units will comply actually to what we decided at the beginning as our success standard. So then this is related to the safety risk, the reliability gap, because engineers, they're mostly talking about reliability. They want to ensure that their device work well and so on. The safety risks include, like, how can we compare it, let's say, with what the FDA or WHO has put as a standard, also our internal standards, and then compare it not just with our reference standard and making sure that we are actually still within the government standard. So a very smooth introduction, just because I'm going to repeat this term very often. So in statistics, we know these 3 pillars: the confidence interval, the prediction intervals, and the tolerance intervals. What are the difference on those? So I tried to put it here color-coded as well in regards to the name. so you can identify it quickly. So confidence interval is mostly answering where is your true average. So let's say we're talking about the height of the people in this room. What is the average height of these people? Then we're talking about this confidence interval. The limitation of the confidence interval is that the more samples you use, let's say like in this room we are 20 people, I'm taking 5 samples of the people, I'm asking the height of each of you, I have the mean, I have the confidence interval, it will be quite large because then it's only a small proportion of the real population. So that the more you increase the number of samples, the more it shrinks. So when we want to check a quality, and this shrink values doesn't give us any kind of information because the more you edit sample size, actually it shrinks so that something can seem to be very different between one to the other, the groups itself. Well, in reality, it's just because we're just talking about the precision of our estimates. The second one is the prediction interval. So you can see the blue part here. It's already slightly wider compared to confidence interval. And in the prediction interval, it happens because we start thinking what is our future measurement will fall. So this is, we're talking about prediction for just a new single observation. So in this case, the intervals become wider because then we start taking into account as well the individual variation because we would like to estimate the future where it might fall. And the third one is our superstar for today's talk is the tolerance interval, this green area here. So this is the widest range of intervals that we have because instead of just talking about the future one single observation, we are now increasing a bit more to a specified proportion of the future observation. So in this case, like let's say I want to estimate 90% of my future population, 99% of my future population, and then this increase of the proportion will also increase the width of your intervals. So the confidence interval I mentioned before, this is something you might heard already as well. Something said like 95% confidence of my true population lies within this calculated range. And as I mentioned, the increasing number of the samples will make the interval shrink toward a certain point, which is then your true mean. While in the prediction interval, in relative comparison here, the relative comparison here, so this is confidence interval, and this is your prediction interval for the individual expectation in the future. So it's slightly wider already. And then the tolerance interval, you normally will see these two numbers, which then the second part still doing the same job as confidence interval. You want to be 90% confident that at least 90% of your population falls within this range. So as a statistician, we normally call it a beta-gamma tolerance interval because then you have two parameters, the beta and the gamma, which one talks about the proportion and the other one talks about your confidence. So this is a bit just to summarize what we were talking before, the difference interval type, how you use it, if you want to focus on one of this stuff, the width itself, and how they behave with the increasing number of the samples. So now in reality, why then us industry is not really able to work with a confidence interval? Because just as I mentioned before, comparing just means with the confidence interval might lead you to a false positive when you are doing design comparability. Because the two design, they can certainly have the mean performance, the same mean performance. So I give an illustration here. So you can see that the blue, let's say that is your new design A, and then the orange one is your old design. And when you're just looking into the mean, you say like, I'm good. They share the same mean, but you forgot the most important part is one design is more varied compared to the other. Meaning that, let's say, what we desire normally in the industry is like having less variability as possible to ensure that we deliver what we promise, but then what if you introduce a new design that actually is not really as precise as the first design? So with this kind of measurement of just looking at the mean and confidence interval, you're not going to see this kind of conclusion in your results. So then why tolerance interval? We see that it's more fitted when we're talking about quality. So unlike the traditional statistical tools that you only focus on the population average, tolerance interval also give you, address directly how big, how the proportion of your population is actually meeting this criteria that you set. So in the sense of quality, it gives us the two understanding, what range covers the certain proportion of my units and with kind of confidence. So you still have these two parameters that is very communicative when you want to talk about risk management. So then when you are accounting for the sampling errors, additional variability, then your tolerance interval actually will be able to quantify what is the likelihood that your product measurements will stay within the limits in the proportion of the population. So normally we work with the specified large fractions, or around 90 or 99%, depending also on what kind of quality, what kind of rigorousness you want to do, that you want to make sure, because like, for example, some stuff, some parameters that you consider that it is not really health hazard or not so important, then you tend to lower down as well the proportion of the population. This is also a standard that is already required in regulated industry. You have the ISO number here. And now we are going to the case study. So in this case, what we are trying to do is that we are testing two different kind of groups. We have the blue body here, which is our new tested product, and the red group is our reference product. So what you see here is the dots representing the individual measured value for the aerosol parameters delivery. On the x-axis here, you are seeing the puff. So it's from the first experience, the puff number 1, until the end of experience number 11. We have 10 different sticks per group. So each sticks have 11 puff. Then the question comes, does the new design delivery aerosol components of our tested products, can we consider them comparable to our reference product? And you can see here, if you're just ignorantly applying a linear regression, you will ignore this movement that it goes up a bit, going down, and then go back up again at the end of the experience. So statistically speaking, we're fitting this generalized additive model with the smoothing spline to let as well the trend to fit in the model, to fit in the self in how the dynamic or the polynomial dynamic of our data. So you can see here the solid lines that we have here are talking about the average with 95% confidence interval on the shaded line. So coming back to what we discussed before, when we're just looking at the average and the standard deviation, for me, this looks like a completely two different product actually. So now what we are doing is that we do two different kind of approach. So the first one is this point-wise tolerance interval, where you are estimating a tolerance for each of this puff. So then you don't really treat the data as a pattern. So you are just fitting, for example, for the first puff, what is the range of my tolerance interval, the second puff, and so on. And this tolerance interval is built on our reference product, because we try to compare to see like where is the location of our tested products against what we should expect as the 95% confidence and 90% of our population, how they will generate aerosol over the 11 puff. So the red dots here are still the reference part, and then you can see that the green one now is the confidence in the mean and the confidence interval for our reference, for our test groups. So the second part is then we are also looking at simultaneously using this profile-wide coverage. We're still talking about 90% population with 95% confidence. And this time we're seeing it as a pattern, as the whole polynomial model. So the solid line still talking about the fitted gum curve for each of the group. So you have for the reference, you have for the test. I included as well now the pointwise, and then the green part, this white green parts is the simultaneous tolerance interval. You might wonder why now when I consider the whole pattern of the polynomial model, I'm ended up with even wider intervals. This is happening because then you also included a variability on how the pattern would look like in the model. So instead of just like focusing on each of the path, now you are also looking at the possibility of how actually my pattern would look like if I'm doing the experiments the next time. So when you're looking actually at the simultaneous tolerance interval and your reference data here with the test data, if we are just looking at the confidence interval, you say, it's good, our product is completely different, we deliver less aerosol in the test product compared to the reference. Well, in reality, then, if you start looking at how the pattern of the path over the 11 path for what you expect in 90% of our population, then you are still actually within what we expected for the reference group. And in this case, you can say that we made the changes, but it somehow is still comparable to our reference product. So this part is explaining a bit more why the simultaneous is wider, and then to make sure that they are actually not just taking into account the individual variability on the path, but also the entire delivery profile. And then we can conclude that our fitted curve for the tested product is still within our reference of the simultaneous band, which then confirming that these two products, we still confirm that they are comparable. The practical workflow, I hope now we get out a bit of the statistical part. How we can do this in reality, first what we did is then we fit the nonlinear model in our data. You can do anything, Kar. So this technique is actually coming from a paper, I forgot exactly the year, but the idea is that you're using this bootstrap for the simultaneous, building the simultaneous tolerance interval. So that makes it fit easily to any kind of nonlinear data. Let's say you have just a smoothing spline, you have brain cousins model and so on. You can fit them and calculate them easily in any of this nonlinear model. And then afterward, we compute the tolerance interval using the reference data of your data set. You choose the number of the population coverage you want to cover, the confidence interval, and then from that chosen coverage and confidence interval, you will be able to calculate the K factor for each pointwise and simultaneous tolerance interval. For me, I always work better with the graph so that I will overlay the plots for the new design, for the reference, for the curve, for the simultaneous and pointwise tolerance interval. And the favorite part is then you can get into the result interpretation. So it is a bit going into the mathematical details, because how the tolerance interval is calculated is that you have your prediction at X, and then you give this K factor that I was talking before, and you multiply them as to the noise level, which is actually what we statisticians like to call it as a variance standard deviation. But in this case, I call it just the noise level because it can come from anything. It can come from your batch variability. It can come from method variability. So any kind of those variability, you capture them in this noise level. And the problem with building this tolerance interval, since we have two proportion and the confidence interval, how do we determine the k so that it really makes sense that we are not overestimating, we are not too conservative and make very wide intervals, and at the same time not to make it too small as well, that we are actually underestimating our reality. So this is just the difference between the point-wise and the simultaneous one. And in the point-wise, you can easily solve the equation because it's just 1 point per point. So it's actually like a traditional way of calculating tolerance interval. But in simultaneous, since especially now we are dealing with nonlinear model, we cannot just solve the equation in a closed form. So then we need this bootstrap simulation in order for you to find a large enough k that will be able to capture your noise in your data. I'm not going to go to this into the detail, but it's just there so that in case you're interested more in the mathematical part, you can have a look and come back to this presentation. So this is actually the paper I was talking about from Guo and Yong in 2024, where they're proposing this point-wise and the simultaneous tolerance interval, how they are, how the integral is solved. So for the point-wise, you reach the k through an integral problem, and then it's a bit more computationally straightforward. While in the simultaneous one, it becomes more complicated because then your probability looks like this. So what happened is that they described this bootstrap algorithm where first you extract the residuals from your fitted model. That's why you can do it with any kind of nonlinear model. You resample and then refeed again your model based on by adding into the extra residuals that you obtain from the first step. You do a kind of a grid search, so you give in your command that you would like this range of k to be looked into, and then what happened is that for each grid of the k, you will estimate what is you obtain as the proportion and the confidence. And then this algorithm will be repetitively done in order to find what is the optimal k that actually will minimize this function. So when you have no clue yet about where should your k factor would be in your simultaneous tolerance interval, I would recommend to go a bit wide. So in my case here, I was doing the search between 0.5 to 6, which is quite large. Just to make sure that I'm actually not finding an optimal k. Let's say if you just run from 0.5 to 3 and then you start like, oh, 3 is actually already my optimal k, and then you stop there. Well, actually, if you expand a bit more on your grid search, you will find that your k is actually larger than that. The conclusion and takeaway is that the confidence interval, again, it's answering more on a question of average. It doesn't mean it's not useful. In the industry, we are still also using this one. When you just want to see, let's say, like during the batch release, you want to know what is your population parameters in terms of average and standard deviation, whether we meet the target that we set or not. Prediction intervals, use this if you want to answer the question, where will my next just one single observation unit will fall? And the tolerance intervals is answering, apart from the future performance, we're also talking about the proportion of our future observations. Practical tools. I'm coming from the generation who's still work heavily with R. And the nice things about it in R that we have already quite a mature ecosystems for tolerance intervals. We have these built-in packages that you can readily use with the tolerance MGCV function that you can use for GUM model fitting. This is to extract the variance component if you're interested more in what is the variability between the sticks or between the experience or any residuals variation. This is just to fit linear mixed models if then you're not so sure whether my data fit with the nonlinear model or not. Try to find the similarities in Python. So what I saw is that it has a growing support more and more as well for the kind of a statistical model, including as well the tolerance interval. So I found that you can run the same with the stats model, where you can use it for non-parametric regression and also to get the confidence bands easily. You also nicely have this GUM model in Python, so you can do this using the PyGum function, and then NumPy or Spicy, that you can then do the custom bootstrap for simultaneous tolerance interval, and then of course with the graphical or visualization part. Just to a bit of the refreshment, the 4 steps of the workflow, we always start with the model fitting. We compute the tolerance interval, either it's pointwise or simultaneously. You overlay what you observed as a fitted model over the pointwise, over the simultaneous one, and you see where your data is, and you can then interpret the results of your data that you have collected. That's it. Thank you very much for your attention.
Do you have any questions? Yes.
Hello, thank you for your talk. I would like to ask you a more generic question. You mentioned you fit the model and do other stuff after that, but generally speaking, how do you choose this model? Based on the graphs or based on some tests like Kolmogorov, for example's test? Yeah.
That's a very good question. I was not expecting that anyone will ask a question in the first place. It's a really nice question because, as I mentioned before, sometimes you don't really know what to expect. So it really depends case per case, because you can also go to literature review if they have already mentioned it somewhere. In this case of this puff per puff aerosol deliveries, it's something new for us as well, because before we don't really look into it, because as I mentioned that we just tend to like something easy, linear regression, that's it. But as you can see that this is not really fitting. For our older product, we actually thought that the brain quiescence models is more fitted because you have this hook effect. So if you are familiar, let's say with the drug discovery, that's how they find the dose, because like you assume that at the small dose, they will give a smallest effect. And then as you increase the dose, you will find the optimal dose deliveries. And then the more you give the dose, you actually just kill them. So we thought at the beginning that our aerosol deliveries is more in this case, so that it will climb up slightly at the end of the experience. Of course, you have less compounds. But in more and more cases of our new product, especially after we are changing the way we heat the tobacco, we observed that it changed completely, and that's why now we would tend to work more with the gum, because then it gives the flexibility in the future to anticipate as well that we no longer follow just a certain pattern to give a bit more of this flexibility. Thank you.
Else?
Thanks, Dea, for a nice presentation. One question about how sensitive is the tolerance interval related to the sample size? Because when we compare tolerance with confidence, we have that issue in the confidence interval, right? So the sample size increasing, we get narrower. Sometimes we overestimate. What is this question in tolerance interval? Is it also sensitive?
That is an excellent question. So, of course, in any kind of statistics, the more you take samples, the narrower it becomes. But tolerance interval is less sensitive to it. So comparing, let's say, a confidence interval, if you're just taking samples of 5, it will give you really huge estimates. And then if you go normally, we say, normally when you started collecting samples about 30 or 50, then normally it gets narrower and narrower. In a confidence interval, the nice part is because of these K factors that goes in function with the number of the population you observed and the number of the samples that you have. So it's in balance of these two. And what is nice about it is, of course, when you only observe 1 or 2 samples it becomes super wide, so that you normally end up with a factor of 6, even 20, sometimes if your samples is really, really small. But then normally it's stabilized even from 10 until 30, the decrease is really small. So we are talking about, because in statistics, maybe it's familiar for you about this 3 sigma, that it means like 99% of your population is within this interval. So it's like that you barely go really small, like 1K or 2K. So it just becomes, the decline becomes very, very small. So from 2.8, 2.6, 2.7, as a K, instead of that drastically, you end up with 0.5, let's say, because of the increasing number of the K. So I did once the simulation for this, even with 100 samples compared to, let's say, 17 samples that you have, 17 samples, it's just declining between 3.8 to 2.8, 2.7, 2.6.
Anything else? Any more questions?
Thank you for the presentation. So can we say that the tolerance intervals are more measuring the uncertainty in the data, and the confidence intervals and predictions intervals are measuring more the uncertainty from the model?
Correct, because I think that's a very good summary for the difference of the two, because the confidence interval, we are just estimating the parameters of our model. So you can say so that it's just measuring the uncertainty around these estimates, while the confidence interval, the tolerance interval, you're also interested in the other possible variability that you might face in reality. Mm-hmm.
Questions? Okay, thank you.
Thank you.